This is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss the problems on the arithmetic and the logic operations. So, before going to the problems on arithmetic and logic operations, we will have a look on the basics of the computer, digital computer system. So, a computer is an electronic device that can be programmed to uh, accept the data input, process it, and generates the results. So, the computer it is basically an electronic device, and that can be programmed to accept the input data. After accepting the input data, it will process certain operations on that given input data. Then it generates a results. Then that generated results will be given to the user. So that is a operation of the computer. So the most computer systems, from the embedded controllers found in automobiles and consumer appliances to personal computers and mainframes, have the same basic organization. So that means these processors or controllers we are using. So these most computer systems we can found from the embedded controllers that found in automobiles and consumer appliances to the personal computer and the mainframes. That means these type of computer systems we are using from a small applications to the large applications. So these all these types of applications we are using the same basic organization. Okay. So if you look into the organization of the computer, so the digital computer system, mainly it has three functional parts or three primary subsystems or components, that are CPU, so central processing unit. So the CPU, it consists of three parts. One is the ALU, arithmetic and logical unit, control unit, and the registers. And the second subsystem is a memory subsystem, and third one is the IO subsystem. So we will see what is the operation of all these subsystems in next further slides. So all these subsystems, they function together as a single unit to deliver the desired output. So by operating all these various subsystems together, so that the required functionality of the computer can be achieved. Okay, so this is a basic computer organization. So the mainly this basic computer organization, so it is having three parts. One is the central processing unit, and second one memory subsystem, and third one IO subsystem. So these are the essential parts of the computer. So CPU. So what it will do? CPU. So the CPU, it performs various operations on the data which is stored on the registers of the processor. And control unit. So control unit, it is used to generate different timing and control signals, because the computer is a combination of various modules. Okay, so all that modules needs to be working in synchronization with all other modules. So for that purpose, the synchronization signals and the timing signals are generated by this control unit. Okay, so and next ALU, arithmetic and logic unit. So this arithmetic and logic unit, it performs various arithmetic and logic operations. Arithmetic operations include addition, subtraction, multiplication, and division. Similarly, the logic operations are AND, OR, NOT, XOR, XNOR, so like that. So we can perform some logical operations. Okay. So in addition to this control unit and the arithmetic ALU, so we have some registers also inside the CPU, registers. So registers are used to store some information. So that may be a temporary that may be a temporary value or intermediate results. So all that we can store in the registers of a processor. Okay, and so this is about the CPU. After that, the memory unit. So memory unit it is also an essential component because we are storing. So suppose if the CPU wants to process something, then the data will be originated from the memory, and also once the CPU accepts the data from the memory, it will process again that generated results also it may store in the memory. So for that purpose, so in order to store the programs and the data, we require the memory unit. And the third one is the I/O subsystem. So I/O subsystem, it includes the I/O devices and the input devices and the output devices. So this I/O subsystem, it provides an facility to interact with the outside world, because the computer it will accept some input data from the external world. Okay, so the input device. So through the input device, the computer can accept the input data from the external world. After accepting, then the CPU will process the data. Then it will generate the results. So that generated results will be given to the user through the output device. Okay, so this is the basic computer organization. So if you come to the arithmetic operations, so the binary arithmetic, it includes the basic arithmetic operations of addition, subtraction, multiplication, and division. So these are the basic arithmetic operations: addition, subtraction, multiplication, and division. So the following sections represent the rules that apply to these operations when they are performed on binary numbers. So when we are performing all these arithmetic operations, we need to follow certain rules. So let's see what are its rules. So when when you are performing a binary addition, okay, binary addition is performed in the same way as addition in decimal system, and is in fact much easier to master. Binary addition obeys the following four basic rules. So here we have shown four basic rules. So this is a one. So when we are adding any two bits, 0 plus 0, so it gives 0. Similarly, 0 plus 1. So if you are adding 1 to the 0, it results a 1. Next, 1 plus 0, it results 1. Next, 1 plus 1. So it gives a 0 with carry 1. So that means you will get 1 0. Okay, so these are the basic rules. So by using these rules, we can perform the binary addition. Suppose if you are adding 1 1 and 1 0. So 1 plus 0, you will get 1. Next, 1 plus 1. So you will get 0 with carry 1. Okay, so this is a binary addition. So here, see, one more example: add 111 and 101. And the second B bit is 10 110 and 0 1 1 1 1. So we are going to add these binary numbers. So consider the first one. So we are adding 111 with the 101. So these are the two binary numbers given. So we are going to add. So if you add this 1 plus 1, so what you will get? You will get the result 0 with the carry 1. Okay. Again, we are adding 1 plus 1. So what you will get? You will get 0 0 with the carry 1. Okay. So see here. So what you will get? So 111. So if you add 1 plus 1, you will get 10. Here one more 1 is there. So we are adding. So you will get 1 1. So here you will get the output as 1 and the carry is 1. So this is an answer. So this is a way of adding two binary numbers. And coming to the second one, so the first number is 10110 and the second number is 01111. So these are the two binary numbers that we are going to add. So 0 plus 1. it gives 1. So using the previous rules, 4 rules are there we have. Okay, so 1 plus 1. So you will get 0 with the carry 1. So if you add triple 1, then you will get 1 with the carry 1. So if you add 1 plus 0, 1. Again 1 plus 1. So you will get 0 with the carry 1. Next 1 plus 1. So you will get 0 with the carry 1. So this is a carry. Okay. So this is a binary addition. And coming to the binary subtraction. So binary subtraction is just as simple as addition. So subtraction of one bit from another obeys the following 4 basic rules. So similar to the previous binary addition, here also we have some certain rules we need to follow that. So when you subtract 0 from the 0, you will get 0 as the output. Similarly 1 minus 1, so you will get 0. 1 minus 0, you will get 1. When you subtract 1 from 1 0, so you will get 1 with the borrow of 1. Okay, so these are the rules. So when doing subtracting, it is sometimes necessary to borrow from the next higher order column. So the only it will be necessary to borrow is when we try to subtract 1 from 0. So we are taking the borrow only if we are subtracting 1 from the 0. So in that case only we are considering the borrow from the next higher order column. Okay. So 1 0. So 1 0 means that is 2 in the column being subtracted. The following example illustrate the binary subtraction. So here you can see how we can perform the binary subtraction. So first one, so we are subtracting 0 1 from the 1 1. Okay. So from the rules of the from the binary rules, so 1 minus 1, so it results 0. Next 1 minus 0, it results 1. So the answer is a 1 0. Next coming to the second one. So we are subtracting 1 0 from 1 1. So 1 minus 0. Okay, you will get 1. Next 1 minus 1, you will get 0. Coming to the third one. So 1 0 0 0 1 1. So 0 minus 1. 0 minus 1. So here we need to bring the carry from the next higher order column. So where 1 is there, so this is a 1 is there. So this 1 we are bringing as a borrow, so that it will become 1 0. So 1 0 means here it is equal to 2. So that means suppose if you 2 is there in decimal, so if you convert into binary, 2 1s are 2. So remainder is a 0. Okay, so 1 0 means 1 0 it is in binary, so that is equal to 2 in decimal. Okay, so when you subtract 1 from the 2, it results 1. So that's why see here when we borrow, when we take the borrow from this, you will get 1 0. So 1 0 means 2. 2 minus 1, you will get 1. Okay, so here 1 is there. So 1 minus 1, 0. Next, already this 1 is taken as a borrow. So here 0 is there. Here 0 will be there. So 0 minus 0. So 0. So finally you will get the result as 0 0 1. So in this way we can perform the binary subtraction. And coming to the binary multiplication. So the binary multiplication is performed in the same manner as the decimal multiplication. So this binary multiplication is similar to the decimal multiplication. It is much easier since there are only 2 possible results of the multiplying 2 bits. The binary multiplication obeys 4 basic rules. So first one is the 0 multiplied with 0. It gives 0. 0 multiplied with 1. It gives 0. So 1 multiplied with 0. 0. So if you multiply anything with 0, it gives 0 as the output. And when you multiply 1 with 1, then it gives output as logic 1. Okay. So using this 4 multiplication rules, then we can perform the binary multiplication. So here we have some examples. So first one is multiplying 101 with the 11. So when you multiply the number with 1 first, so this is called multiplicand. This is called multiplier. Okay. So we are taking the first digit in the multiplier. Then that first digit we are multiplying with the multiplying of the multiplicand. So if you multiply anything with 1, it gives same that number. So you will get 101. Next we are multiplying with another 0. So you will get the same 101. Now we are going to add. So what you will get? So this one. So 0 plus 1, 1. 1 plus 0, 1. Next 1. So this is the result. Similarly, second example. So 1, 1, 1, 0, 1. This is a multiplicand. And multiplier is a 1, 0. So first we are taking the 0. We are multiplying the multiplicand with 0. So you will get all zeros. Okay. Next we are multiplying the multiplicand with 1. Okay, with 1. So that you will get the same as multiplicand. So 1, 1. Okay. 1, 1, 0, 1. Okay. So now the result is 0, 1, 0 plus 0, 0, 0 plus 1, 1, 1, 1. Okay. So this is a result. Coming to the C bit. So 1010 multiplying with the 101. So now we are multiplying with 1. First we are considering the multiplier. So in the multiplier, first we are taking the this rightmost bit. Then this with this bit we are multiplying the multiplicand. Okay. So you will get 101. When you multiply with 0, you will get all zeros. Okay. Then we are multiplying with 1 now. Then you will get 1010. Okay. So now we are going to add all these bits. So here 0, 1 plus 0, you will get 1. Here all zeros. Next 1 plus 1, you will get 1 and carry 0. You will get sum as 0 with carry 1. Next here 1, 1. Okay. So in this way, we are performing the binary multiplication. Now coming to the binary division. So division in the binary number system employs the same procedure as the division in the decimal system. Okay. So here, in order to understand, here considering a binary division. Okay. So we are dividing 1110 with the 11. Okay. So 1110 we are dividing with the 11. Okay. So this is a 11 is a divisor. So this 11 it will be go in one time. So one time. So 11. Okay. So the remainder is a 0. So we are taking this 0. Next, if the 11 is multiplied with 0, you will get another 0. So finally you will get the 0 as the remainder. Okay. Now coming to the B, so here we are dividing 11 with the 11. Okay. So 11, so it will be taking one time. Okay. So 1 1. Next it will gives the remainder as 0. Then we are taking 1 0. Again we are multiplying with 0. So you will get a 0. Next remainder is 0. We are taking another next 0. Okay. So in this way we are performing until we get the remainder as 0. Okay. So this is a binary division. And coming to the logic operations. So the digital logic has 3 basic operators that are AND, OR, NOT. So these are the basic logic operations. So using these basic logic operators, we can form some other logic operations that are NAND, NOR, XOR, XNOR, so like that. So these are the basic gates. Using that we can realize any other logic operation. So these three operators form the basic for everything in digital logic. So in fact, almost everything your computer does can be described in terms of these three operations. Okay. So the first one is the AND operation. So the symbol for the AND operator is a single dot. So this AND operation we can describe with a single dot. So single dot. So here we have mentioned. Okay. So a mathematical expression using AND looks like this. Okay. So here you can see the AND operation. So in order to perform this AND operation, we have two bits. We have two bits. So here in bit A and B. So A and B are the two inputs. So on the two inputs we are performing this AND operation. So see here. So the alternate notations for AND are AB, A and B, A and B and A cap B. So we can represent this AND operation in different ways. So you can use any notation. So see here. So when the input bits are 0, 0, it gives the result as 0. Similarly, when inputs are 0, 1, it gives 0. When inputs are 1, 0, it gives 0. When inputs are 1, 1, it gives 1. So that means if any input is logic 0, then it gives the output as logic 0. So that is an AND operation. Okay. So the symbol for the AND operation will be, it will be like this. So this is a A and this is a B and it gives the A and B. Okay. So this is an AND operation. Now coming to the OR. So the symbol for OR operation is a plus sign. So using the plus sign, so OR operation. So plus sign is used to represent the OR operation. So the mathematical expression using OR looks like this: A plus B, A plus B. Okay. So the alternate notations for the OR are A or B, A or B, A parallel two lines B. Okay. So this is a OR representation. So if you look into the truth table, so A and B are the two different inputs. So when inputs are 0, 0, it gives 0 as the output. Similarly, if inputs are 0, 1, it gives 1 as the output. Similarly, if inputs are 1, 0, it gives 1. If both inputs are 1, 1, it gives the 1 as the output. So that means here in AND operation, if any one of the input is logic high, then the result will be logic 1. So the output will be 0 or logic low only if both the inputs are zeros. Okay. And the symbol for the OR operation will be okay. So this is the OR symbol. Coming to the NOT. So NOT is a unary operator, so which requires only the single input, while the and OR are binary operators as they require two values as the input. So this NOT gate, it is having only the one input and one output. So if you assume A is the input of the NOT gate, then the output of the NOT gate will be A bar. That means it will gives the complemented of the given input. So if you give the input as 0, it gives the output 1. Similarly, if you give the logic 1 as the input, it will give the output as a 0. So that means it will complement. It will perform the complement operation. Coming to the NAND NOR. So if the NAND, NOR, OR and NOT operations are combined, then the NOR and NAND gates can be created. So using these three basic gates AND, OR, NOT, we can realize the NOR gate or NOR operation and the NAND operation. So NAND operation. So what is NAND? So NAND is a complement of the AND. So A into B whole bar. So that is equivalent to the NAND operation. So this is a inverted operation of the AND gate and the NOR gate. So NOR gate is first we are performing OR operation, then we are taking the complement of that, so that you will get the NOR operation. Okay, so it is the inverted output of the OR gate. So here you can see the truth tables for the NAND. So if inputs are 0, 0, you will get 1. If inputs are 0, 1, you will get 1. If inputs are 1, 0, you will get 1. If inputs are 1, 1, you will get 0. So that means in previously NAND gate, if any input is 0, the output is 0. But here, if any input is 0, the output is 1. So this case. So in these three cases, if any input is 0, output is logic high. The output will be only high when all inputs are logic 1. So that is a NAND operation. Coming to the NOR operation. So what is the OR operation? So NOR is a complement of the OR operation. So in OR operation, if any input is logic high, then output is logic high. But here it is a complemented. That means if any input is logic high, then output will be 0. Okay. So see here. So in the second, third, fourth case, so if any input, so here 0, 0, if any input is logic high, then the output will be 0. So output will be 1 only if all inputs are logic zeros. Okay, so this is a NAND and NOR operation. Okay, so coming to the problem, consider the following example in which we will perform bitwise AND operation between the two numbers 2 and 6. So we have a two numbers, one is number 2 and 6. So in between them we are performing the AND operation. Okay, so first we have to take the binary equivalent of the 2. So what is the binary number of the 2? 0, 0, 1, 0. So if you we are considering here a 4-bit number. So that's why 0, 0, 1, 0. For 6, so 0, 0, 1, 1, 0. So these are the binary representations. Okay, now we are performing the AND operation. So what is AND operation? If any input is 0, then output is 0. Okay, so we are comparing these two bits. So both are zeros. So output will be 0. Next, 1, 1. If both inputs are 1, then output will be 1 in AND operation. Remaining case 0, 1, 0, 0. So this is an AND operation. Okay. Coming to the second one, consider the following example in which we will perform the bitwise OR operation between the two numbers 2 and 6. So we are performing OR operation. Okay. So what is OR operation? See here. So looking to this OR truth table. So if any input is logic high, if any one of the input is logic high, then the output will be 1. So output will be 0 only if both the inputs are zeros. So using that rules, then we can perform this OR operation. So see here. So this is a binary equivalent of the 2 and this is a binary equivalent of the decimal 6. Okay, so 0 plus 0, it gives 0. 1 plus 1, it gives 1. 0 plus 1, it gives 1. 0 plus 0, it gives 0. So this is a OR equivalent. After performing OR operation, the result. Consider the following example in which we will perform the bitwise NOT operation. NOT operation of an integer number 3. So we are performing NOT operation on the number 3. So first this 3 number we have to convert into the binary. So binary means so binary equivalent number is 0011. So 0011. So then after that we are performing the complement NOT operation. That means NOT operation is means so if the input is 0, then it will be converted into 1. Then if the input is 1, it will be converted into 0. So that is a NOT operation. Okay, so that after performing NOT operation, it gives 1100 as the output. Okay. So the decimal conversion of 0011 is -4. So 1100. So in sign magnitude representation, that is equivalent to the -4, because if the MSB bit is 1, that represents a negative number. Okay, and the weightage of this 100 is a 4. So that's why -4. And coming to the example 8. So consider the following example to perform a bitwise XOR and XNOR operation between the two numbers 10 and 13. So here two decimal numbers are given 10 and 13. So in between them we are performing XOR operation and XNOR operation. Okay. So first, so 10. So how we can convert this 10 into the binary? So the 10 equivalent binary is a 1010. 1010. So this is a binary equivalent of decimal 10. Similarly, 13. So binary equivalent of 13 in decimal is 1101. So using the 8421 code. So 13. So 13 means by adding the weightage of this, that will be equal to 13. So 8 plus 4, 12 plus 1, 13. So this is a equivalent to 13. Similarly, this will be equal to 10 because 8 plus 2, 10. Okay. So in this way, we can write the binary number. Okay. So now in between them, we are performing the XOR operation. What is XOR operation? So if the inputs are different, that means if 10 is there or 01 is there, then it will be gives the 1 as the output. So these are the inputs. This is the output. Okay. So if the inputs are same, then the output will be 0. So this is a XOR operation. So using these rules, so 0 plus 1. Okay, 0 plus 1. That means inputs are different. So that you will get the output as 1. Next, 1 0. Inputs are different. You will get 1. 0 1. You will get 1. 1 plus 1, 1 1. So that means inputs are same. If the inputs are same, what you will get? You will get the 0 as the output. So that's why 0. So this is a XOR operation. Similarly, we can perform the XNOR. XNOR operation is the opposite operation. It is a complement of the XOR. Okay, so this is XOR. This is XNOR. So in XNOR, if different inputs are there, then you will get the 0, and if the same inputs are there, then you will get the 1 as the output. Okay. So see here XNOR. So how we can get the XNOR? So using the same two inputs, see 0 1. So 0 1. That means inputs are different. If inputs are different, then you will get the 0. Okay. So 0 0 0 1. So this is a XNOR. Okay. Next example 9. So consider the following example to perform bitwise NAND and NOR operation between the two numbers 10 and 13. So already we have seen how to convert the decimal numbers into the binary. So 10 equivalent binary number is a 1010 and 13 equivalent binary number is a 1101. Okay. Okay. So this is the 10. in decimal, 13 in decimal. So this is a binary equivalent. Okay, so now we are performing the NAND operation. NAND operation. So what is NAND operation? NAND operation is a complement of the AND operation. Okay. So NAND. So in AND operation, if any input is 0, output is 0. But here, if any in NAND operation, if any input is 0, the output is 1. So here 1. So here 1. Here 1. And here 0. Because if both inputs are 0, if both inputs are 1, 1, you will get 0. Okay. And coming to the NOR operation. NOR operation. So what is the NOR operation? So NOR operation is a complement of the OR operation. So what is OR operation? So if 0, 0, 0, 1, 1, 0, 1, 1 are there, so then output will be, so in OR operation, if any input is logic 1, then output will be logic 1 and output will be logic 0 only if all the inputs are logic 0. So NOR operation is a complement of that. So 1, 0, 0, 0. So that means if any input is logic high, the output will be 0. So here 0, 0, 0, 0. So output will be 1 only if all inputs are zeros. So this is performing how we are performing NAND and NOR operation. Okay. So in this lecture we have seen how to perform various arithmetic and logic operations. So the arithmetic operations are that are addition, subtraction, multiplication, and division. Similarly, we have seen various logic operations that include and, or, not. So these are the basic operations. So using these basic operations, we can realize some other logic operations that are NAND, NOR, XOR, XNOR. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.